So I think we're live.
Okay. Cool. Right. Right. Okay. Hello, everyone. I'm James Hopgood. Good to see you here for this talk. So I'm the chair of the IEEE UK and Ireland section, and today we're kicking off an early careers research seminar series. So we have our two speakers, Dr. Shuyan Lee from Queen's University Belfast and Dr. Xinming Shi also from Queen's University Belfast, and they're going to be presenting in a while. Each of their talks will be about sort of 30 minutes long, and Shuyan is going to be talking about training-free event-aware video anomaly detection, and Xinming is going to be talking about evolutionary brain-inspired computing systems based on Memristors. So I'm going to give an introduction just while we're waiting for everyone to join. I'm just going to give an introduction about the IEEE UK and Ireland sections. Some attendees might have heard of this before because if they've been on previous talks, and also about the purpose of today. But just before we get into that, do note that we are going to record these seminars because we have set up a YouTube site where we're going to capture as many of seminars as we can. So just be mindful. The way that Teams works is that we're capturing this via Teams, and you end up with sometimes it shows, sometimes it doesn't. We're still working it out. The little screenshots of people who are on there. So just be mindful that if you do turn on your camera, that you might get recorded, and similarly, but at the same time, when you ask questions at the end, just be aware that you're being recorded. Okay. So also make sure we're keeping an eye on this, but just make sure that your microphones are muted if you're not talking. Just you get all the fun things where people get telephone calls or plumbers arriving in the middle of a seminar. If something goes wrong, so we're aware that sometimes with Teams that if you can't see the screen, because depending on how we share, whether it's usually if you share screen, everything's okay. But I know some presenters share PowerPoint directly, and then that sometimes I know because I've been through it, but you can't see the screen. So if something doesn't work, just pop out the meeting and pop back in because that often resets the problem. So we'll be monitoring and just letting everyone in. So don't worry about that too much. If you do want to say something later, just make sure that you've checked your speaker and microphone settings so we don't have that issue of just talking to a screen. And then for today, the talks will last between an hour and an hour and a quarter, and we'll take questions after each individual talk. Okay. There is a Q&A box. I don't know if you can see that. So if you can see the Q&A box, feel free to ask any questions at any point. So just as a reminder, I mean, most people know about the full IEEE Signal Processing Society, which was one of the first IEEE societies, and back in 1948, and I think it had its, see if I get my maths right, I mean, it had its 70th birthday a couple of years ago, and I imagine that there'll be some 75th celebrations coming up soon. Today it's got 23,000 members in 120 countries. For the UK and Ireland section, we're about 600 members. On average across the year. And the activities that we do are we try and support conferences, workshops, we get distinguished lecturers. We're having this as a early career research lecture program. And there are other things that we get involved in as well. At the moment, committee running it are myself as chair. And then you heard George speak a moment ago when he was saying we've gone live. So George is the secretary and treasurer, and Lugan, who has leading this sequence of talks, is from the University of Bristol, and both of those are online. So we're kind of running it. So feel free to reach out to us. We are going to do a call for people who want to give talks to the IEEE signal processing sector. So we'll be doing that over the next month or so. So just a reminder, the purpose of the chapter is to serve IEEE members. That's why we're going to send a call out, because ultimately it's about holding meetings that are actually relevant to its membership and that are useful to them. And we do, when we have in-person events, then that provides opportunities for networking, research, potentially forming project collaborations and so forth. So we're working on those. But for our particular committee aims for this year was because the chapter was a little bit dormant for a few years. We have started off light, and we started off wanting to showcase local achievements from across the UK and Ireland signal processing communities, basically to sort of build or rebuild the map of signal processing activity. So especially in the age of machine learning, where computer science departments and other departments do potentially lots of signal processing work. And so there's an element of finding out, of reminding everyone where there was substantial activity happening. We, sort of want to communicate more with its members, and we're always open to ideas. So we are going to try to set up a feedback loop so that you can come back to us with ideas that would be of interest to you. We're still working on sort of co-opting committee members and friends of Signal Processing Society. So they will be people, friends of SPS would be, for example, colleagues who can help disseminate event talks, to sort of try and publicize it more so that we can get a lot more attendees than the reach that we've got. We're quite aware that the IEEE e-notice is not particularly effective, mainly because it's probably overused, and LinkedIn has some capability, but it's quite limited. So what we really need is friends who help sort of circulate it amongst our research groups or departments. So just where we've been for the last year, we've had a couple of major talks so far. So Wenwu Wang from University of Surrey kicked off a new series of hybrid talks, which we're aiming to run roughly every 2 months. On Signal Processing Birthday Day, which was the 2nd of June, Asok Nandi from Brunel University gave a talk, and I think our next sort of talk in that series will be the end of September. But we also have intermixed with that something that's very important to all the committee, and that's bearing in mind that with early career researchers, it can be quite hard sometimes to give lots of talks to the signal processing community, perhaps because of sort of potential barriers. Some researchers are much more mobile than others, so there can be barriers if you've got lots of caring responsibilities. For example, being able to travel around the UK on the seminar circuit is easier said than done. So what we've set up is we'd like a series of online, basically hybrid online talks, just online talks for early career researchers aimed at new lecturers, postdoctoral research associates, fellows, PhD students, and so on. We're also very keen to promote and highlight contributions of women in signal processing. And there is a Women in Signal Processing Society, and we're sort of currently liaising with them to see how we can sort of get mutual benefit from these early career research talks. We're trying to support some conferences, workshops, so on. So it can be everything from the Signals and Systems conference that took place in Ireland. I think it's either early this year or coming up. I actually can't remember the dates. But also other workshops that happen around the country. There's one in Edinburgh, which is coming up at the start of September, which is on the MSIG, the Electromagnetic Special Interest Group, and they're hosting. So we kind of co-host as part of that event. We are planning, or haven't organised it yet, but we are planning more talks on how to go about getting senior membership applications, because they're quite low across. I've got a slide in that in a moment, and we're trying to get involved in distinguished lectureship talks. Yeah, so a portfolio of events will be put on a website soon. But yeah, just on that issue of senior membership, so you can become a senior member after you've got, I think it's 10 years of being involved in IEEE, or maybe not in IEEE, but 10 years involved in the sector. And we have a very large proportion of members who are eligible for senior membership but haven't actually taken it up. So if you look at this these bar graphs here, where blue is members, and so just for those, everyone in blue should be able to move to the yellow band. So we want to increase the number of ratio of senior members to other membership. So we will help trying to think of ways to help try and explain that process. It's much simpler than you would expect. So we want to try and help explain and support that where we can. Okay, so that's me just introducing. So I'll just give a moment if anyone wants to actually raise a question on anything I've just asked, just been talking about. Right, so I'm just going to stop sharing that for a moment and we'll just get ready for the next speakers. So I'll just give an introduction to each of the speakers. So just while we're doing that, Shuyan, would you like to bring up your slides for the talk?
Sure.
Just make sure that's up and ready before I give you an introduction.
Okay. Yes, I can make a brief introduction for myself.
Oh, okay. Well, I was going to introduce you, but
if you, I don't want for James to have an introduction, and then so Shuyan, you can start.
Yeah,
presentation. Yeah.
Okay. Right. Just give me a second because I've just had a tech failure with the document I had open, which were my notes. Give me a second. Sorry, just tech failure. Just my Word has crashed. Anyway, we'll just give it a minute anyway for other people to join.
Okay, so.
And oh, just give me a second. So I've got my computer's just crashed very badly. Right, well, I tell you what, let me just because I'm having trouble with this. I'm going to introduce Shuyan, who's a lecturer at School of Electronics, Electrical Engineering and Computer Science at Queen's University Belfast. And you can see on Shuyan's slides already that she started in that role back in June of last year. And so really welcome to have this talk. And so I think, Shuyan, I'm a bit more, bear in mind you've got this slide up. I don't want to gazump you too much. So I think I'll hand over to you and maybe you can go back through your sort of track record, your background of your PhD when you did that and working at the Department of Engineering in Cambridge. But delighted that you can present this talk. And so over to you.
Okay, thank you so much, James.
Actually, if possible, could you please turn on your video just for the first few minutes just to introduce yourself?
Okay. Okay, so hello everyone. Now you can see me. I am Shuyan Li. So as introduced by James, I graduated from Tsinghua University and now I am assistant professor in AI at Queen's University Belfast. My research field span across a broad area in artificial intelligence, which consists of video understanding, unsupervised learning, unsupervised domain intelligent method to some interdisciplinary applications. For example, the construction digital twins, medical imaging, and materials. And I am very thankful for the invitation from the IEEE Signal Processing Society. And today I want to introduce a current work for you, which is just accepted by the ACM Multimedia. So the authors of this work come from a variety of institutions. For example, the Beijing University, Tsinghua University, Jingdong, and also the Queen's. And I also invite the first author, Yihua Shao, to this meeting. And after my introduction with this work, and if you have any technical questions, Yihua will answer for you. Video anomaly detection focus on the identifying anomalies within videos. So this row of the video depicts the normal scene. For example, the streets, there are many people in the streets. However, for example, suddenly a bike just appears in the street and go into the people, so it will be anomaly scene. And also, you can see the third row. You can see the third column. So for the avenue, a man just walk in the wrong direction instead of those way. So this will also be determined as an anomaly scene. So the task of the video anomaly detection is to detect the anomaly frame and detect where the frame is, and detect where the anomaly object is. The general framework for the video anomaly detection method is that, well, we will extract the features from the video and also develop a model to produce the anomaly scoring based on the extracted features. And then a threshold will be applied to the anomaly score to produce the frames and locations of anomalies. There are a variety of ways to develop the video anomaly detection. For example, we can use the fully supervised way, and we can also only annotate one class, and we can also use the weakly supervised, and there are also some unsupervised ways to do the video anomaly detection. However, for the supervised method, we know that it is infeasible to manually annotate so many videos, and it cannot be applied to the real-world applications. And for the unsupervised methods, it will usually based on some very fragile assumptions, which will make the result be less accurate. So overall, the training-based methods are prone to be domain-specific. That's been costly for practical deployments, as any domain change will involve data collection and model training. So instead, our work will focus on the training-free ones. The training-free methods will leverage the modality-aligned vision language models to query and enhance the anomaly scores generated by large language models. However, there are some limitations for the training-free large language model-based methods. The first one is that most training-free methods is to do the image-based anomaly detection. And this series of methods will fail to capture the temporal dynamics, which will cause the inconsistent video predictions. And the second limitation is that it usually adopt the multi-stage VQA pipelines. It will remain storage and computation inefficient. So how to solve these limitations? We observe that the normal sequences maintain relatively uniform interframe relationships, while anomalous sequences exhibit distinct discontinuous at abnormality occurrence. And this demands a segmentation mechanism capable of amplifying these continuity signals. So if we can detect the continuity signals, we can segment the video into several events instead of treat it as separate frames. That will decrease the computation cost and the storage cost, and also to increase the temporal consistency among frames. That is the major motivation of our proposed event VAD. So it enhances the existing methods for the temporal consistency by processing the segmented short events while employing dynamic graph models to capture interframe relationships. And finally, we can achieve higher precision anomaly detection with reduced parameters. Our framework consists of 4 components. The first one is to construct the event-aware dynamic graph, and the second one is the graph attention networks propagation. And these 2 components is to capture the temporal information among the frames in the video. And then the third component is the statistical boundary detection. And this is to detect the boundary among the videos. So it will be used to segment the video into events. And after the event segmentation of the fourth component will be the event-centric anomaly scoring. So we can produce the anomaly scores based on the segmented events. So the first component, event-aware dynamic graph construction, is to address the limitations of static graphs in capturing dynamic events and the slow training of graph neural networks. We propose a dynamic spatial-temporal graph model based on the video frames. In the graph, the vertex site means that corresponds to enhanced encoded video frame units. And the edge of the graph denotes the dynamically established through cross-modal similarity measures. And the mode representation employs a dual-stream architecture integrating both semantic and motion branch patterns. So with the graph, we can capture both the semantic information and the motion information within the video. After building the graph to improve the frame-by-frame representation while preserving temporal consistency, we propose a training frame attention mechanism based on orthogonal feature projection in spacetime. And this mechanism amplifies segment contrast through graph-guided message passing, enhance the event boundary distinguishability. So with the graph attention networks propagations, when there's anomalies or when there is some abrupt shift among the videos, the boundary will be distinguished, and then it will be easily to segment afterwards. So based on the graph, we propose a statistical boundary detection mechanism to identify the event transitions via temporal discontinuity analysis. We compute the composite divergence metric with the following equation. The first term amplifies the abrupt feature space jumps to ensure the attention respects event induced, and the second cosine term detects directional changes in the manifold. So this dual strategy captures amplitude and the directional discontinuities caused by anomalies. Since there will be some noises, so we apply a filter to smooth the output. Then we can get the statistical boundary. After we get the boundaries, we can segment the videos into several events. And we propose a semantic-driven event anomaly scoring framework. In this framework, the videos are divided into discrete event units, and there are two two-stage prompting for multimodal large language models. The first one is the event description generation, and the second one is the anomaly scoring based on these descriptions. And after that, a self-correcting inference reduces the hallucination errors and enables precise frame-level anomaly localization. And after that, we do the experiments on two public data sets. This is the experimental results on the UCF crime data set. As you can see that our proposed method achieved the state-of-the-art AUC with significant advantages over the above methods. So our methods outperform all the training frame baselines. Also, when compared with the supervised one and unsupervised one, we can see that our method outperform all single class and all the unsupervised method, and we achieve competitive methods against the weakly supervised methods. And the experimental results on the second data set, sorry, the title is wrong. On the second data set is as follows. So we can see that the event VAD significantly outperforms the current training frame SOTA methods at all single class and the unsupervised methods. And we achieve optimal AP and AUC scores. This demonstrates the effectiveness of our proposed methods. And when compare our method with the LAVAD is the first training frame method, and we can see that our method outperform the LAVAD, and also our method has much less parameters. So the LAVAD has 13 billion parameters, and in comparison, our method just has 7 billions. We can see the qualitative results of our methods. So on the UCF crime data set, there are some abnormal things in this video sample. We can see that for the first scene, the supermarket was checking out normally when suddenly two men came in and looked ill-intentioned. So someone just entered the supermarket, and the scene is not so abnormal at this situation. So the score produced is not very high. But then one robber took a bag and took a lot of stuff from the supermarket, and another robber forced the cashier with a gun. So this is very abnormal, and our model produce relatively high abnormal scores. And for the second sample, it's a normal sample. So the video just shows a restaurant with a room full of tables and chairs, and some people just enjoy their meals in this video. So for the normal video, our model just produce a 0 score. So it means that we did not detect any anomalies in this video. And for the third example from the XD violence dataset, we can see that at the very beginning there will be a abrupt abnormal scenery. So this shows that a controlled demolition process where a large concrete structure is being demolished using the explosives. And then the explosives end, and the video shows an aerial view. So the anomaly just appears. And the final sample is also a normal examples, and our model successfully detect that there is no abnormalities. We have uploaded our codes on the GitHub for the people to download. So if you want to follow our method and if you have any questions, you can just upload your issues on the GitHub, and we can give you feedback. And also, if you have any questions for my current for our works, you can it's the time for you to ask the questions. Thank you.
Okay, brilliant. Thank you. Thanks, Shuyan. I'm
You're
looking
welcome.
I'm trying to do. I like to do we can do a clap. Everyone's microphone's on silent, so you won't be able to hear them clapping. Great, that was really interesting. Thank you. So I'd like to open the floor to questions. You can also, if you don't want to speak, you can also put questions in. Hang on, I don't know how you do this. Let me put any questions here, see if this works. But would anyone like to ask a question either in the chat box or in the chat box, or just unmute, or put your hand up first as the easiest thing. Maybe I'll start off with a sort of question, just to start to get going. So I mean, what I found interesting about this talk was the sort of combination of the MLLM and some, if you like, what I'd call sort of almost traditional statistical signal processing approaches. I think it was slide 12 with the statistical boundary detection approach. And I suppose, I mean, a couple of questions. One is, have you done kind of an ablation study where maybe you're looking at what the most important thing was that distinguished this from the Lavid method? So, for example, on I think it's slide 12, where you were detecting the boundaries of different sequences. I mean, I'm kind of, having heard the talk, assuming that this made quite a difference. And then the question is, you know, there are different sort of, if you like, change point analysis methods in the literature, and how much does the method that you've used on the statistical boundary detection have an impact on the result? So if you used a slightly worse statistical boundary detector, does that significantly significantly change the performance of the algorithm? Yeah. So how much does the boundary detection play a part in the overall system?
Okay. So your question is that how much improvement is introduced by the event compared with the frame-based detection, right?
Yeah, or any other kind of, rather than using the divergence metric on the screen, but presumably other metrics you could use as well.
Yes, we might have a ablation study table in the paper, but let me check. Or Yihua, do you have? Let me check.
Oh, okay. Maybe I could share my screen.
Oh yeah, go ahead. Although, let me just check. George might need to try and share the screen, Shihao. But if it doesn't work, George might need to make you a presenter, which is okay.
And maybe just need to wait for a moment because my network is not really good.
Okay, but you can describe it verbally if you like, for the moment.
So the main question is the boundary detect. What is the main factor of the boundary detection, right?
Yes, yeah.
Okay, and I think the main factor of the boundary detection is that the graph attention, because because as the evolution study have shown that when we ablate the flow, and it's not really it is mean with the feature of the image. And after ablation with the graph attention, there is no the model has no has lost the ability to detect the boundary, so it couldn't slice a whole video into a different event, and maybe it will like lava that slide the videos into different events with a single frame.
Okay. Okay, great. Yeah, that answers. I think that answers my question. Okay, great. Now, I think did I see someone else's hand go up? Does anyone else have a question they'd like to ask?
Yes, it's me. Hello.
Hi, I can hear you. Yeah, just go ahead.
Yeah, this is really impressive work. Thank you for this presentation. I would like to ask you about the evaluation metrics. I can see here that you used the AUC, which is area under the curve. So I would like to ask you why you choose these evaluation metrics especially, or or do you recommend something else to be used in the future, or that's all. So why did you use the AUC especially, and if you recommend any evaluation metrics in the future?
Okay, and because as for the fair experiment, the lava test has used the AUC and the AP for environment metrics, so we have followed the setting with as the lava, and so I think this will have the more fair computation with this baseline. And
So
as for the better evaluation metrics, as the IEEE submission, I have reviewed a paper with the event-based stream anomaly detection. Maybe I think that will propose some more reasonable benchmark or the evaluation metrics. Maybe after I have finished my review, we could have a deeper discussion.
yeah, so you did use the AUC in order to compare with other works or previous research papers. Is it correct?
So sorry, I haven't
Sorry,
heard clearly.
I'm sorry. So you used the AUC as an evaluation metrics in order to compare with other previous research papers. Is it correct?
Yes, that's right.
Yeah. Okay. So, by the way, this is very informative presentation. Thank you, and the paper as well. Thank you so much.
You're
Thanks.
welcome.
Great. Okay, brilliant. Thanks for that question. And yeah, do we have any more questions before it's time for one last question? Let me just check chat box. And just to say, if anyone who does ask a question, I'd probably encourage you to follow up with just drop the presenters an email afterwards, just so at least they know who you are, and you might want to follow up. But always good to show interest. Okay. All right. We'll move on, and if any other questions come up later. But thanks very much. So let's just thank Shuyan again as our speaker. I'll do a verbal clap. Okay. Thanks so much. Okay, so our second talk is from Xinming, who is also from Queen's University Belfast, where Xinming is an assistant professor, and Xinming got her PhD in computers. Hi, yeah. If you just want to give you a brief intro, if you want to put your screen up. So Xinming had a PhD in computer science from University of Birmingham in 2023, and she's going to give us a talk on what I think is going to become quite a really important area in signal processing and machine learning, and that's a brain-inspired intelligence using neuromorphic computing hardware and software, and sort of how Memristors come into this as part of the evolutionary brain-inspired seems to be gaining lots of attention. There was a Xinming sort of knows earlier, there are different research groups around UK and Ireland who are looking at this area. So it's really exciting to hear about how Memristors as an electronics technology is really changing how we do compute. But Xinming, do you want to? Sorry, you just check you shared your screen. Yeah, I think over to you, really.
Okay. Thanks for Jen's introduction. Can you hear me clearly?
Yeah, I can hear and I can see the screen, so everything's good. Yeah, and I can see
Okay.
most importantly, I can see the laser pointer, which is
Thank you. Thank you. Yes, I really appreciate to have this opportunity to share my work. The topic is about the evolutionary brain-inspired computing system based on memristors. And this talk may give a whole figure of this research. And yes, and they already introduced this about myself. I graduate from University of Birmingham and also have some visiting experience in Victoria University of Wellington and South Tech. And now I'm a lecturer in Queen's University Belfast and working in neuromorphic computing. So the first, I'll give a very brief research background, mainly about brain-inspired computing and memristor-based system design and evolutionary computing. And our brain is a very powerful and efficient computing system, and it have a lot of good mechanism like sparsity, learning, variety, and knowledge. And in terms of the architecture, the brain has a high degree of parallelism and low power and high computing density. So we want to get some inspiration from not only the mechanisms and also the architecture to create a more efficient computing system. And from the mechanism part, we want to create a computing system that is efficient and based on analog computation, real-time processing, and also low latency decision making and fault tolerance and so on. And from the architecture part, we want to use memristor to create hierarchy circuit design and also to make it more compact. And we also use the evolution computing as automatic approach to help us automatic design these kind of circuits. And in terms of the algorithm part, we also want to use the evolution approach to further evolve the function to make it not only have the learning ability, but also have the evolution ability. And this research has been regarded as the UK's 50 emerging technologies for these biologically inspired AI. And we can see there is a very obvious contradiction between the computation power of chips and high requirement for training. And from this figure, we can see the growth in performance of chips recently grows very slowly, only 3% per year. But the requirement of the computation power for training increased really fast. Right now, it like 3 to 4 months doubling. And why we have this contradiction? It may because of these three bottlenecks. The first one is the device bottleneck, and the second one is architecture bottleneck because we use the von Neumann architecture. There are a lot of latency and energy consumption for this architecture, and also the energy efficient bottleneck. So we require the new devices, new architecture, and new system to tackle these bottlenecks. And the memristor is the key element we use. It has been predicted in 1971. Lemtra predicted the existence of this circuit element, which is memristor, and more and more researchers has been attracted to this area. And in 2008, HP company fabricated the first physical memristor. And also some non-volatile and volatile memristor devices has been created. And the Memristor have several key advantages like memory characteristics and multi-value, and can integrate the storage and calculation into one device. And it can fabricate into this array architecture. And further, we can construct this Memristor-based in-memory architecture and can solve like the device bottleneck, architecture bottleneck, energy efficiency bottleneck, and further to implement some brain-like information processing architecture, and can simulation the working the brain-inspired working mechanism, and also can do the hardware acceleration circuit to improve the processing efficiency. So we say like memristors may offer the possible solutions for those bottlenecks. And we also want to draw some inspirations from nature, like our brain is not created in this intelligence level. We evolved for many years to have this intelligence level, and this is how we evolved from like 90s of 1994 and to right now. We also want to evolve some brain-inspired computing systems. And this is overall framework that how we create this evolutionary brain-inspired computing. The first part is about the brain-inspired computing architecture, and also we create the evolutionary algorithms, and then we have some key applications like speech recognition, image recognition, and like some other optimization tasks. Okay, so the main contributions of this research mainly related to these aspects. So the first part will be some basic units, and then will be the architecture implementation. And based on the architecture implementation, we propose some reconfigurable hardware and also some automatic design approach, and also its applications. So I will start from the basic units here. And in our brain, the synapse and the neuron are basic model. So the one single memristor could be used to emulate the synapse. And the memristor crossbar could be applied to map the weight matrix of neural networks. And there have been a lot of work and researchers to this area to use the memristor to emulate the synapse function and use as the weight metric. And also this one is a very simple or basic neuron model, which is leaf neuron. And we can use these dynamics and the memristor dynamics to mix them together to use the memristor to create the neuron model. And this work is about the use memristor to create to implement the synapse and neuron with the homostatic plasticity. And we use memristor to model this homostatic threshold variation, and also to implement a neuron with the adaptive firing rate. The homostatic plasticity is a kind of strategy that can trade off this weight potential and also weight depression to trade off this not too high or too low for the firing rate. And we use the memristor to further implement this function. And we also create some different types of neuron circuits that with this homostatic plasticity. And in order to verify this neuron, we verify it into this Bonotnik function verification, and also in spiking neural networks. And for this part, we use the our proposed neuron in the output layer, and to help the spiking neural network do not have like the overtraining or undertraining issues. This is how it works. This is the firing rate can adaptively to adjust to inherent range of firing rate. And we also compared our proposed circuits with other neuron circuits, and our proposed one also have better power consumption and better area. Okay, the next part will be how can we use the proposed neuron and the snaps to create the architecture. And in our brain, we follow like this hierarchy architecture. So when we want to create this memoristic architecture, we also follow this similar strategy. We create this bottom layer, middle layer, and top layer that have different function to implement the memoristic computing architecture. For our work, we focus on the spiking neural network and also evolutionary algorithm. Use the memoristic architecture to implement these two kinds of algorithms. Okay, this part I've already introduced. We use the Memristor crossbar as the weight matrix, and also we use our proposed Memristor neuron as the output layer neuron to help us get better performance. And how we train this simple memoristic neural network, we just use the simplified STDP rules. And this shows some of the results to verify our work is workable. Okay, the next part, the next algorithm is about the evolutionary algorithm. This is the framework or flowchart of how an evolution algorithm is implemented. Normally, we have the parents and also the offspring. We use the parents and offspring to array to interact together and to help the parent array to be updated to the optimal one. And due to the fault tolerance of the evolutionary algorithm, this architecture is very fault tolerant and can evolving and adapting continuously even in the presence of hardware failures or changes. And also in terms of the speed and energy efficient, because of we use this Memristor element and architecture, which is very energy efficient. So our proposed work is have better energy efficient and speed. And for this work, we the further step of this work, we want to use the physical platform to implement the evolution algorithm and try to use some real platform to verify our proposed demo or algorithm and hardware is workable and can integrate advantages of Memristor array, such as in-memory computing and sparse and approximate computing. This is the slide that shows some of the results. And this figure shows that even there like the 42 hardware damage for the Memristor crossbar, it still can have some good results. And also for the sparse and updating of the Memristor array, we can see that not all the Memristor will be updated. Only the one that we located by our strategy, it will update it. So this could show the show the sparsity and the approximate computing of our proposed architecture. Okay, so for the next part will be evolutionary reconfigurable architecture. Because our brain is not created, it evolved to the current intelligent level. And we also want to evolve not only the weights, but also the architecture and rules to further create these evolvable brain-inspired computing systems. And we mainly focus on these two different types of reconfigurable architecture. The first one is the 41R reconfigurable architecture, and the second one is the 1R reconfigurable architecture. And for the first one is that why we call this 41R is like this basic unit consists of 4 transistors and 1 memristors. And we further extend this reconfigurable unit to a platform with like this 41R architecture. And then we further use an evolutionary approach to evolve this reconfigurable architecture to make it have different topology to support these different connections. And why we want to have this evolvable topology is that the fixed or random topology of reservoir computing is not good enough. And we want to have a adaptive strategy or approach to help this reservoir part could be evolved to get better performance. And our proposed the architecture can give the basic foundation or physical foundation for these reservoir circuits. And our proposed evolution algorithm can be used to apply to this reconfigurable architecture to help this architecture get different or different and evolvable topology. And this is the some topology we evolved. For the different tasks, it has different kind of topology. And also we do some noise injection experiments. And we can see because of this 41R architecture, the variation of memristor is limited because we only use the nonlinear current of this memristor, and the variation is acceptable. And we also use this architecture to do some time series prediction tasks and also get some good results. And another one is 1R architecture evolution. And this one, some colleague may know that 1R architecture have the sneak current. Is like that. If we want to update the memory resistance of this element, and the current will not only flow in this way, maybe flow in this sneak current, sneak pathway. So this we normally regard this as the drawbacks of 1R architecture. But in our work, we do not regard these sneak currents as drawbacks. We regard this as the benefits. We can further evolve these sneak currents to help this architecture or this crossbar have better or different dynamics.
有點太恐怖了都。
Sorry, you have questions? Oh, okay.
So you mean just carry on? I think that's just the mic not being muted, so I'm just going to mute that participant.
Okay,
Yeah.
okay. Yes. Yes, the evolution algorithm operates by evolving the configuration of the memristor crossbar both in different ways. And we can get the robustness and efficiency of the whole computing systems. Okay, this is kind of how these currents evolved by our proposed approach. And finally, we will get a good configuration for this 1R crossbar. Okay, so besides this hardware or hardware or architecture thing, we also propose some automatic design approach, which is if there is some automatic or AI approach can help us to design the circuits, not all by human or all by some people with experience. So we use the genetic programming to help us to design the circuits instead of manual design. And we use this tree-based representation to evolve these circuits. All the circuits, this is how we represent the circuits by a tree. And we propose this tree representation, and then we propose a framework using genetic programming, and then some evolutionary operators help us to evolve these circuits. And then the evolved results have the better performance than some human design and also some other automatic approach. And this one is we use our proposed approach to evolve a memristor-based circuit, which is a memristor-based spike circuit. And then we can get this kind of results. This is the input of these circuits, and this is the output of the circuits. And the red line represents the actual curve, and the green line represent reference curve. And we can see that there have very small differences between the target and the actual output, and all by our proposed automatic design. And we can see that we can get better area and better energy efficient. Okay, these show some sample of evolved circuits, may be a little different from manual design, but it also works. And this one is the further version of this genetic programming work. Okay, so the next part is talking about some applications. This one is about the explainable AI, and we use our created evolvable memoristic circuits to help it have better explainability. And we can see the memristor crossbar may be regarded as the black box. And then if we use our evolution approach, we can further help us to do the feature attribution, and we will know which feature will be more important. And this one is how we get these. This one is generated by our proposed framework. Okay, this is some future further steps of this work. And beside that, there is another issue I'm really interested is about the long-term dependency work, because there are a lot of large language model that to tackle this issue, but the large language model may be too large and rely on a lot of computation power. And if the neuromorphic computing can propose some possible solutions, this is our first attempt to this issue. And we create this kind of higher order time delay and implement by memoristic circuits. And then we further implement into the memoristor crossbar and to try to tackle some prediction tasks, and we can get some good results. But this is the first step. And this will be our next step, that there's some other large language model which is inspired by brain, like Matmu-free algorithm and also the Spike SSM. We want to implement this large language model, brain-inspired large language model into this Memristor platform. And also there's some other multi-scale modeling thing that will also be our next steps. Okay, thank you. I will stop here, and this is my LinkedIn homepage, and this will be on my another homepage. And if you have any questions, feel free to ask me or email me. Thank you.
Okay, thanks, Xinming. We could do everyone could unmute their mics if they liked, but that could cause chaos. Thanks so much for a wonderful talk.
Thank you.
And it's really interesting to sort of see the sort of intersection of what is new, effectively new sort of circuit design technology with AI, and the fact that this technology is being used to directly build new architectures and so forth. It'd be great to sort of take some questions from the audience before we finish. So again, just try and use the chat box or raise your hand. No, that's I think just while people are thinking of questions, I think I was quite interested by I think it was back on slide 38 or something about explainable memristor computing circuits. I suppose could I get you just to expand a little bit on what does it mean to be to be explainable? So what kind of criteria are people looking for in terms of explainability? Because I think explainable AI sort of has very different interpretations.
Okay, thanks for your very good question. And this one is because some people like we do not know what is a memoristic computing system and why it is work. Because maybe some edge intelligence need this memoristic computing architecture or system for like healthcare or some other significant scenario. So we want it trustworthy and why it is work and the decision making it is trustworthy or explainable. The users may also have these questions, and our approach give these questions some possible solutions. We use this evolution framework to help the user or to help the user to understand why this memoristic computing system is work. We can get some good results. It is work, but why? So we use this. We follow the feature attribution, this key technique part, and we use the evolution framework to implement the feature attribution of this memoristic computing system to help the user understand which feature is important with the varying time. And we can see these different results indicate the different tasks. Like maybe they not show, maybe this one is some industrial time series. And we can see this darker part will be more important to help the user to know, okay, this part will be more important and like this feature will be more important. Try to give some indicator of why this memoristic computing system is explainable and why it could be trusted. I'm not sure if I answer your question.
No, you did. I think it's very interesting. I think there's quite a, so you can sort of see analogies of sort of working out which features are important in other sort of analysis of neural networks. So I also get the feeling that there's quite a lot of additional background which interested researchers need to get on top of to understand all of that. But yeah, very, very interesting.
Thank you.
Okay. Are there any questions from the audience? Okay. We don't get many questions on online talks as but I think if we do, George has got a question.
Yeah, thank you, Shi, for your presentation. It was very informative. Just a quick question. It's a bit more broad. It's often the case with spiking networks that the processing latency kind of depends on the achievable firing rates. So I would like to ask you more or less what's the current state in terms of Memristor-based spiking networks in terms of their capabilities of the achievable firing rate, or their speed in broader terms.
Okay, thank you for your question. Yes, so we normally want to find, we know the spiking neural network have their advantages compared with other like conventional computing networks. But we still want to find some killer application of this of spiking neural network. That's what that is one of the try to find the advantages or benefits of the spiking neural network. Because you mentioned the question is a very important issue, like, but the memristor but the spiking neural network is have the good results in like DVS or some event-based cases that will be more efficient and more energy efficient, and also the very fast speed in terms of these kind of applications. And you mentioned also about the memristor implementation of the spiking neural network, right? If I
Yes,
understand, yeah. Yes, so from my current work, we not only use the memristor to do the snaps of spiking neural network, but also we use the memristor to do the neuron part. And then we can further implement or integrate the memristor, the neuron and the snaps into one memristor crossbar. That will more efficient in terms of the latency issue and other efficient energy issue.
So would it, let's say, reach a firing rate in the order of some megahertz, or we're talking more biologically closer in the order of hertz? If you have some more specific number on that.
Okay.
Other than that, I'm pretty much covered.
Yes, right now I'm using Memristor to implement a leaf neuron. I'm not sure if you know about this neuron model. It's a basic neuron. It's a basic model for spiking neural network. It can simulate or it can emulate the some of the dynamics of biological neuron.
Yeah. Okay. Thank you so much.
Welcome.
Okay, thanks, George. Thanks, Shuyan. Okay. Any final questions? Okay, in which case, I think I'd like to thank both the speakers again for both putting together a presentation and especially keeping them relatively short, because it's very easy for, I think you could have spoken for another hour. Each of you could have easily had an hour-long talk, but it's fantastic that we've been able to hear two very different areas. So yeah, thanks very much for taking the time to do that, and thanks everyone who's attended for taking the time to come and attend and to listen to the talks. And and we'll soon be advertising sort of for expressions of interest for future early career researcher talks. So we'll be in touch about that through probably e-notice in some way. But thanks very much. Enjoy the rest of your afternoon, and let's just give a round of applause either virtually or with your hands if you want to. Okay, thanks. Okay, bye everyone.
Thank you.
Thank you.
Thank you.